Yes, today we are still on identifying various types of fingerprint. Identifying various type of fingerprint. And in the last two modules, we discussed about the first group. We said we have about three groups, and the first group is arch, the second group is loop, and the third group is wall. We have discussed uh, the first group, which is arch, the second group, which is loop, extensively. And now today we are on wall. So the third group, which is wall, is what we are discussing. So, and if you look at the screen, you can see that there is a lot of difference in the structure, the design of this group is totally different from the first two. And this group, wall, is about 30% of all the fingerprint that you'll be encountering. In the this last lecture, we said loop is about 60%, about 60 to 65%, and the arch is about 10 to 15%. So this group is the second largest or second common out of all the fingerprint pattern. So it's about 30% of all the fingerprint that you'll be encountering when you are working on fingerprint pattern. Now, this group is subdivided into about four. The first one is plain wall. The second one is a double loop, central pocket loop, and the last one is a accidental wall. Now let's talk about this one first, the plain wall. The plain wall has the simplest form, the simplest design of all the wall subdivisions. And the plain wall, we have two datas, as you can see it on the screen. This is data, left data and the right data. So you have two datas, at least two datas in the plain wall. Then you have what they call it, we have a recurve. We have recurves between the data, and this recurve make complete circle. Many of them make complete circuit, and the circuits may be any of the variant of circle, like a spiral, like oval, like a circle. So, but at least there must be a complete recurve, at least a complete recurve before you can, between the two datas, before you can call it a plain wall. So let's move ahead. Before we move further, now if you draw a line from the first data to the second data, from the left data to the right data, the line must cut across one of the recurve that is complete, that form a complete circuit. It must cut across it. So if it cut across it, then you call it at least one. Then you call it a plain wall. This is a plain wall now. This is a plain wall. Then let's move ahead to the next one. The next one we'll be discussing is a double loop. Double loop. Now, the double loop under this subdivision has two loops. That's why we call it a double loops. And these two double loop, somehow they are somehow, one of each of the loops may be somehow similar to the loop you have in the second group, but they are not the same. The double loop consists of two separate loop formations. As you look at it, this is a separate formation of a loop. This is another separate formation of a loop. And two separate distinct set of shoulders. Look at it. You have here, you have shoulders here. This is what we call shoulders. Where you have inner recurve, where you have inner recurve as you have it in the second group that we call loop. You have, this is shoulders. All these are shoulders. This is another shoulders. So they are separate shoulders. It's not that one shoulder is covering the whole thing. So you have different shoulders. Each one of them will have separate shoulders. So also they have two datas. You have a data here, then you have another data here. So when you have that one, you have what is qualified to be called double loop. The loops of a double loop do not have to conform to the requirement of the loop. In other words, we don't use reach count here. No reach count is necessary. So the issue of reach count is not necessary in any of the word. That's why the fact this one is called double loop. So we don't use reach count here. So what we use here in any of the word is known as ridge tracing. We will be coming to that one later. So the decision between twin loops and lateral pocket loops, we are coming to that one later. Let me skip that one. So one thing I would like to point our attention to is that it is not necessary that the two loops be equal. They don't need to be equal in length, nor that the two loops be of the same size. And it is immaterial from which side the loop enters, whether the loop enters from the right or from the left. That one is immaterial. All we need is that we have two separate loops that have these separate shoulders, and also two datas, at least two datas. Look at it, this is a data here, this is another data here. Then that is what you look, those are the things you look at, and you say you have a double loop. Then let's go to the second. I think you are following me. Let's go to this following, this next design or next pattern that you call central pocket loop. Central pocket loop. Now, in this central pocket loop, if you look at it very well, the central pocket loop has two datas also, and at least one ridge making a complete circuit. Look at it. At least one ridge making a complete circuit. You have a data here, there's a data here, there's another data somewhere here. And at least a ridge or you have a recurve that is complete, a complete recurve, making a complete circuit. Here it may be just only one. So now if you draw a line, an imaginary line between this data and the other data, it must not touch the complete circuit. It will not, or it must not touch a complete circuit. So if you draw a line from this false data and on getting into the data here, wherever you locate your data here, the data of this one is here. So if you draw an imaginary line between these two data, it will not touch the curve that has made a complete circuit, which means that is a central pocket loop. But in the other one, in the plane loop, it must touch. By the time you draw line from first one to the second one, it must touch. But this one, it will not touch it because of the way it formed. So this one of the reason, this one of the indicator that this is a central pocket loop or not, when you draw a line from the data, from one data to the other, from the left hand side data to the right hand side data, and the line does not cross across the curve that made the complete circuit, then you say you have a central pocket loop. In the central pocket loop, one or more of the simple recurves of the plane loop type usually recurve a second time to form a pocket within the loop. You see, look at it. This one recurve to this place, and another one, and it curve again. That is where we call pocket. That is what we call pocket. So in the central pocket loop, one or more of the simple recurves of the plane two type usually recurve a second time, as I said, to form a pocket within the loop. The second recurve, however, need not to be a continuation of or even connected with the first. It may be an independent one. You see, at times, look, if you look at this one very well, if you look at it, you can see that look at this place. This circuit got to this place and stopped. So another one started again. So at times the double circuit may not be connected together. But as long as that circuit, the first one, is complete, a complete recurve, it's a complete circuit, it's a recurve that is complete, that form a cycle, either spiral or over, a complete circuit there. That is one of the characteristics. It has fulfilled the requirement. And then another requirement is double data, and another requirement is that when an imaginary line is drawn from the first data to the second data, it will not touch any of the complete circuit. Let's move ahead. This is a accidental war. In the accidental war, that one has a lot of this is the third formation. It has a lot of structure that is totally different from what we have in the time past. At times, you have in the accidental war, you have double loop combined with an arch. At times, we have two arches combined with a loop. At times, we have two arches combined with a loop. So, and at times you may even have something that does not resemble any one. You cannot categorize it as an arch, as a loop, as any of the formative. So when you have anything like that, we call it accidental war. The accidental war is a pattern consisting of a combination of two different types of pattern, with the exception of the plain arch, with two or more datas or a pattern which conforms to none of the definitions. It may be a combination of loop and tented arch, or loop and wall, or loop and central pocket loop, or double loop and central pocket loop, or other such combinations. So the plain arch is excluded, as it is rather the absence of pattern than a pattern. Underneath every pattern, there are ridges running from one side to the other, so that if it were not excluded, every pattern but the plain arch will be an accidental wall. Look at it. This one has the first one has double loop. This is combination of double loop. Look, then it must have at least 2 datas, but this one has 3 datas. This a data here, this another data here, this another data here. Then this one has combination of arch. This is tented arch plus double loop, and here we have a data, and also we have a data formation somewhere here. Now look at this third one also. The third one has arch. It has arch, tented arch, and a loop. This is a loop on its own, and this arch, tented arch. So now with ridge tracing, in the second group of ridge pattern, in the second group, which is loop, we use ridge counting. We say ridge counting is an important, a vital tool to have a positive identification. The same way, in war, what we use instead of ridge counting is ridge tracing. Ridge tracing. And how do we do ridge tracing? The first thing is to look at my screen. The first thing is to locate the data, at least 2 data, the right data and the left data. This is the right data here, and this is the left data here. Now, if the data the data at the left hand side has a formation of bifurcation, as you have it on the screen, what you need to do is to start tracing from the lower arm of the bifurcation. Trace it down. Now, if that one stop here, then you jump to the next ridge, the next outer ridge, the next outer lower ridge. You jump to it. Then if that one stop abruptly, then you jump to the next one. You move to the next one, move to the next one, until you get to the place where you have the second data. Then you draw a line from the data to this place. You trace it. Then you count the numbers of ridges between the data and the tracing ridge. This last one. So you count the number of ridges that you have there. So the tracing ridge here will be the place where you start counting the number of ridges between them. If the number of ridges between the data and the tracing ridge is 3 or more than 3, maybe 3 or 4 or more than that, then you call it outer ridge, denoted by O. Then, if it is otherwise, let's assume that you have let me go forward. Now let's come here. Now look at it. The first, if you trace from here and you trace like that, on getting here, if you discover that what you have is between the tracing ridge and the distance between the space between the tracing ridge and the data, if you know that, if you discover that you have at least more than 3 ridges, counting the number of ridges that you have here, you will not count the data and the ridge. So 1, 2, 3, 4. This is 4 ridges. So what you have here is outer wall, denoted by O, outer wall, outer wall. Then if you are tracing, as you are tracing, the trace take you to upper part, that is in front of the data. In front of this data, you are tracing the line and take you to upper part. And by the time you get to the immediately is a point immediately after the data, a place that is just opposite of it, you stop. Then you count the number of ridges between this tracing ridge and the data. This is 1, 2, 3, 4. So what you have there is inner wall. Look at the difference. This one is the tracing of this one take you to upper parts, and when you stop at a place that is directly opposite of the data, you have at least 3 ridges between them. You call that one inner. But when it takes you outside and below, takes you below the data. Now you are below the data here. Then the number, and then you have more than 3 ridges. That is outer. But here you have above this. It takes you above. It takes you above the data. This is data. The data here. It takes you above the data. So by the time you count the number of ridges and they are up to 3 or 4 or more than that, between 3 or 4 or more, then you have inner wall. Then another type of wall that you may have is when you trace it in the accidental wall. And when you trace it like this, and after tracing, when you are tracing, you may meet data, 1 or 2 data in the middle. Just ignore it. What you need is the leftmost data and the rightmost data. So you trace it, you trace the line. If you get to this place and this one ends, you jump to the next one, the next outer lower one. You jump to the next outer lower one until it takes you to this place. So if what you have here, what you have where are the last region, the tracing ridge. If the tracing ridge is here, and between the tracing ridge and the data, if you have just only one or two ridges between them, then you call that one mid wall. Mid wall. So in wall, generally speaking, what we use to differentiate them, what you use to make identification, positive identification, is tracing, ridge tracing. But in loop, we use ridge counting. So the ridge count is meant for the loop, while ridge tracing is meant for the wall. Now let's summarize what you'll be learning in these 3 modules. That is the module that talk about identifying various type of fingerprint, identifying various type of fingerprint pattern. So in that, and we talk about arch, loop, and wall. We said all the fingerprint pattern can be categorized into three groups or three families. And the first one is arch, the second one is loop, the third one is wall. And we said that the arch can be further classified into plain arch and tethered arch. Also that the loop can be further classified into radial loop and ulnar loop. We also said that wall can be further classified into 4 groups or 4 subdivisions. The first one is plain wall, the second one is central pocketed loop, the third one is a double loop, and the fourth one is a accidental wall. And we made it clear to us that the fact that you are hearing loop here does not mean they have anything to do with loop under the second group, but that they belong to wall. And we said that in loop, we use something that is very vital for identification, and that is ridge counting. Ridge counting is when you count the number, you locate core and data, and you count the number of ridges between them. And that one can be used to identify, because every fingerprint is so unique that the numbers of ridges, the ridge count of each fingerprint is not the same. It's unique to it. It's not the same with others. So the ridge count is a vital tool in identification of fingerprint pattern. And also in the wall, also the ridge tracing is particularly specific and unique to every wall, every fingerprint. So when you have a wall and you use ridge tracing, you can use that one to identify it or to differentiate from others. And we said the arch fingerprint are characterized by a wave-like pattern. Without wave-like pattern, that is, this is what we mean by wave-like pattern. Without any data or core, they don't have data, they don't have cores, and that is why you don't use the ridge counting them. And the arch is like about 15% of all the fingerprint that you'll be encountering. They are not common, so they don't have a ridge count. You don't use ridge count for them. You don't use ridge count. They don't have ridge count because ridge counting is not possible, because they don't have data and they don't have cores. So, and we said they are divided into 2. You have plain arch or plain arches and tinted arches. So let's move further. And also, we also say that loop fingerprint are the type of fingerprint pattern where one or more frictionless ridges enter one side of the print and curve up and around, then flow out on the same side. Look at it. Look at it. They move from one side, from this side. This one move from one side, curve up, recurve, and come out from the same side. Look at this one also, the same thing. And we said this can be further divided into 2. Either the left slant loops or the right slant loop, that is the radial loop or the ulnar loop. And we said every loop we have core. We have a core and a data. And we said between the data and the core, we have if you count the numbers of ridges between them, then we have what you known as ridge count. So ridge counting involves drawing a line from the core to the data, but the data itself and the core are not counted. They are not need to be counted. You don't need to count them. So let's move. The rules, we said the rules in ridge counting is that you locate the exact point of the core. You try and locate the exact point of the core and that of the data. Then you count the ridge across an imaginary line drawn between the core and data. Then, as you said, you don't need to include the data and the call. Now, last before I move to the next one, the incipient ridges. That is, there are some. If you look at the ridges very well, there are some ridges that are so faint. Those faint ridges that are formed as a result of perhaps maybe a ridge breaks away, or maybe the ink was not properly done. Those ridges, or perhaps maybe because of the mark on the mark of scar of an injury in the hand of the suspect. You don't count those ones. They are faint. You only count those ridges that are thick as others around them. So let's move further. And also we said retracing begins at the top extreme left of the data and stop at the point directly in front of the right data. In an accidental war having three datas, the tracing begins at the extreme left data and goes towards the extreme right data. You just ignore any data you meet along this path. What we need is the tracing. You trace, just draw a line. You start drawing a line from the data. You move it along the ridge. If the ridge stop here, then you start on the next following ridge. You start, if that one stop, you start from the next one also, until you get to a place that is opposite the data. Then you count the numbers of datas between them, ridges between them, and that will give you whether it is outer wall or inner wall. Yeah, this is where we are going to stop today. The knowledge that you have acquired through these three modules, the knowledge is going to be used when we are making comparison between two fingerprints. So please keep this, go over and over again. I will send a note to you. So go over it again. The knowledge will be used later. Will be used later when we get to the module where we'll be discussing on how to compare fingerprints. And the next topic is going to be on how to lift fingerprint from surfaces. Even though as a fingerprint examiner, you may not go to the crime scene to go and lift it, but you must know how to lift. The knowledge of lifting it is necessary for you. So thank you. This is where we are going to stop today. Thank you, and God bless you till we meet in the next class.